here is I'm going to switch to the PowerPoint because I can blow it up a little bit more. Okay, so what we're looking at here is, see this part here where we have the pHs? Okay, so these are actually tracing out the different species and what their concentrations are going to be. In this case, it's in mole fraction. See that? So it's the fraction of the total number of moles. Okay? Okay, so if we go to pH 7, that's going to tell us the different species at pH 7. So we go up, and we see that this is something like right there, right? About halfway between 0.6 and 0.8, isn't it? And so of our population, we're going to have about 70%. That's the free-floating lead 2+. Okay? So no complex ions, nothing like that. Just uncomplexed lead 2+. Okay? And then you would notice here we have two other species that are going to be present, right? And so we'd have the lead phosphate here, which is the solid precipitate. And that would be about 0.2 something, right? Okay. And then we have this one down here, which is the lead hydroxide that has positive charge, which is the complex that'd be soluble. Okay. And these would be your different forms of lead. That's why, for example, like in a Flint, Michigan case, where you had lead oxides in the piping and lead phosphate in the piping, right? If you had pH 8 water, like an alkaline water, it's not much of a problem, is it? Almost all the lead stays as lead phosphate, and so you don't have as much lead releasing. But once you start reducing that pH, what happens? Your free lead starts increasing, doesn't it? And so all of a sudden you're drinking a lot more lead in your water. Okay? You go from almost nothing to 70% of that lead in that form. Okay? So that's why you have to be very careful if you're ever taking a city water supply and changing its pH, which is actually what they did in Flint, Michigan, in case you're curious. Anybody have any questions there? Does it make sense how to read that? It's actually a pretty basic graph once you get used to it, right? You go, okay. Yeah. Okay, so if we were up here, what would that look like? Yeah, you'd just trace up, right? And so this would be your lowest species. The rest of them would be almost nothing, right? And then this would be your next highest species. And then this would be your largest concentration. Okay? This one over here would be about 0.65, 0.7. I'd have to use a paper to trace across, or a ruler to trace across. Everybody got that okay? Okay. Very good. Does anybody know why, as we add H+, we'd start getting more and more lead 2+? That's going to help. The other thing that's going to help is, like, if we add an H+ to this, it's going to go to phosphoric acid, right? You're going to start putting hydrogens on. This will go to a water, right? So you're going to start reacting these things that it would react with. You're not going to have the free OH minuses anymore, which is a large part of the lead population that gets consumed. Okay. And so we have double effect, actually. We have a common ion effect, where we're taking away part of an equilibrium, right? And then we also have the overall ionic charge as well. Yeah. And so, yeah, that's kind of a neat effect. Okay. What equilibrium is going to be governing this lead speciation below the pH 7? So if you're trying to figure out what equilibrium governs this concentration, which one you'd use to figure out that lead concentration at pH 7, what would it be? let's look back at the graph. So we're pH 7 here. Okay, so what's going to be the equilibrium that governs that concentration? I'm actually going to move this back with the question. You guys can actually see that a little easier. Okay. pH 7. There. Okay. What's going to be the equilibrium that governs that?
It's like a fractional 0.7.
Yeah, it's going to be the ones involved in your fractional. Okay, so the equilibrium that governs that lead speciation below your pH 7. So after pH 7, right? Okay, so what happens to this form right here after pH 7? Yeah, it goes away, right? So at pH 7, we don't have to worry about that form. We don't have to worry about this. We don't have to worry about that one. The only ones we have to worry about below pH 7 would be lead 2+ going to lead hydroxide. Okay? And so that's going to be the equilibrium constant for lead 2+ lead hydroxide under pH 7. We don't have to worry about any of the others. Okay? As long as we're below pH 7. If we're above pH 7, up to about here, there would be two different equilibriums, right? It would be this equilibrium and this one. Okay? The most important one would be this phosphate one, right? The dissociation constant for that. Okay? Because that's your most important one because you have the most of it, right?
So is that what that? Which equilibrium is governing?
Below pH 7?
Which one is the most?
It's the most dominant.
Most dominant.
Yeah, the one that gives you the largest concentrations. Okay. Now, interestingly enough, this actually does this flipping, where it's this equilibrium is most important below pH 7, between pH 7 and about pH 9 here. This equilibrium becomes very important, and then it actually flips back to these at this point. So for a short time here, pH 9 something, this becomes the most important equilibrium again. Okay. Okay, let's go on to the next chapter. Anybody have any questions about chapter 8 real quick before we flip on? Okay. If you end up with any questions, please let me know through the homeworks. If you go, oh my goodness, I don't understand how to solve something, Dr. Clausen, what the heck's going on? Please talk to me, let me know. Okay?